Okay, let's dive right into this. Welcome to the explainer. Have you ever actually stopped to wonder how a self-driving car knows a pedestrian is about to step into the street? I mean, really knows it in real time. Today, we're tracing the fascinating, frankly mind-bending evolution of how artificial intelligence learned to understand not just static, frozen pictures, but the continuous, flowing reality of video. We are unpacking the incredible leap from simple image recognition to profound, four-dimensional video understanding. And let me tell you, it's a wild story full of computational bottlenecks, biological inspiration, and some seriously brilliant mathematical hacks.
To really grasp why this is so incredibly complex, just consider this simple question. Is this person sitting down or standing up? If you're looking at a single, isolated frame caught mid-action, the pose is identical. From one static image, the AI literally cannot tell the difference. Zero chance. Without knowing the sequence of events, without seeing the frames that came right before and right after, analyzing a single picture completely fails to capture the reality of the action. Motion direction, right? That's the missing piece of the puzzle here.
So here is our roadmap for today's explainer. We'll start with 1, the curse of time, then explore 2, the naive 2D failure. Next, we'll look at 3, adding the third dimension, 4, mimicking human vision, and finally, 5, the transformer era.
Right. Section 1, the curse of time, also known as the spatio-temporal challenge. Let's start with the villain of our story, which is the literal explosion of data that happens the moment you add time into the mix.
Now notice the stark contrast in the math here. With a single image, an AI deals with a 3D spatial tensor. It's just height, width, and color channels. Pretty straightforward. But the very second you look at a video clip, you have to multiply all of that by t, the time dimension. Adding that extra t takes a standard image processing task and turns it into a massive, four-dimensional spatio-temporal mathematical monster. You're no longer just looking at what something looks like. You have to mathematically model dependencies across an entire sequence. And that extra dimension, it brings severe computational roadblocks. Think about the sheer weight of processing video at 30 frames per second. The storage and memory requirements absolutely explode. Plus, you have this massive temporal redundancy. I mean, 2 consecutive frames look almost identical, right? So you're giving the AI very little new information while eating up huge amounts of bandwidth. Then you've got the challenge of long-range temporal dependencies. An action like standing up spans over several seconds, meaning the AI has to somehow hold on to context over a long sequence of frames. And finally, motion ambiguity. Is the object moving, or is the camera just panning? This created incredible tension and massive mathematical roadblocks for early AI researchers. Moving on to Section 2, the naive 2D failure, or being blind to the flow of time. Let's look at how the earliest deep learning models completely tripped over this whole curse. So the crucial point here is that early on, researchers tried a kind of naive approach. They just took standard 2D convolutional neural networks, processed every single frame of the video completely independently, and then just mathematically averaged the features together at the end. But this had fundamental flaws. First off, it created temporal blindness. Each frame was analyzed in total isolation from its neighbors. Second, by averaging the features at the end, they destroyed the sequence of events entirely. Which brings us right back to our anchor question. If you lose the sequence, the AI cannot tell if someone is sitting down or standing up. It was totally blind to the flow of time. Section 3. Adding the third dimension, treating time as a space. To solve this temporal blindness, researchers decided to try a brute force mathematical solution. They extended the convolution itself right into the third dimension. And this brilliantly illustrates the leap to 3D CNNs. Notice how the kernel, the mathematical filter scanning the data, doesn't just slide over height and width anymore. No, it now slides over height, width, and time simultaneously. So instead of just learning what, say, a hand looks like, the spatiotemporal feature map can actually learn dynamic flowing patterns like a hand moving upward. It explicitly captures the motion right alongside the appearance. Now, this led to a massive breakthrough known as the C3D milestone. By using homogeneous 3x3x3 spatial temporal filters across all the layers and training on a massive dataset of over 1 million sports videos, researchers proved definitively that powerful generic video features could be learned by an AI. However, there was a catch. Actually, a pretty big one. Because the parameter count increased by a massive factor compared to 2D networks, training these 3D models from scratch hit a severe computational wall. The math was undeniably brilliant,
but the hardware at the time just couldn't keep up with the sheer weight of the data.
Which brings us to Section 4, Mimicking Human Vision, the Biological Blueprint. Basically, when pure math got too heavy and computationally prohibitive, computer scientists looked to the human brain for a cheat code.
They were directly inspired by the dual pathway theory of our own visual cortex. You see, human biology splits visual processing into two distinct streams. There's the ventral stream, which recognizes objects and tells us what we are looking at, and the dorsal stream, which processes motion and tells us how things are moving. AI researchers looked at this and thought, wait a minute, why not just build a neural network that does exactly the same thing?
And two-stream networks adopted this perfectly. They created one spatial stream where the input is just a single static RGB frame. This captures the what? The appearance of the person, the colors, the background context. Then, they created a completely separate temporal stream, where the input is a stack of optical flow frames. Now, optical flow is basically a dense field that estimates the exact horizontal and vertical movement of every single pixel between frames. It perfectly captures the how. By processing spatial context and temporal motion separately and fusing them together at the very end to guess the action, they created a highly effective biological mimic.
But, researchers still wanted the sheer power of 3D networks, just without that crushing computational cost of training from scratch. Enter the i3D inflation principle. i3D found an absolutely ingenious step-by-step hack. They took highly successful 2D networks that had already learned all about images from massive datasets like ImageNet, and they literally inflated the 2D kernels into 3D space by just repeating the weights along the time dimension. Then, they cleverly rescaled those weights by dividing by the temporal depth. This allowed them to transfer years of pre-trained spatial knowledge directly into a video model, beautifully bypassing the need to train massive video networks from absolute zero. Building on this biological blueprint even further, we get the slow-fast architecture, which is famous for its incredible efficiency. It uses a slow pathway that operates at a low frame rate, maybe just 4 frames per second, but with very high resolution to capture the fine details of what is in the scene. Simultaneously, there's a fast pathway operating at a high frame rate, like 32 frames per second, but at a very low resolution with far fewer channels, solely focusing on how things are moving. It perfectly mimics human biology to save computation, proving once and for all that you don't actually need high resolution to understand rapid motion. Section 5. The Transformer Era. Solving the complexity. Finally, we enter the modern era. Just as they revolutionized text and images, video transformers take the stage to fully conquer the fourth dimension. But as you might guess, they brought their own unique mathematical hurdles. Let's look at this explosive number right here, 784. If you take a tiny split-second video clip, just 8 frames long, and extract 3D spatiotemporal tokens from it, you get 784 tokens. For a standard vision transformer, the self-attention mechanism has to compare every single token to every other token. That means the attention matrix is 784 squared. That's over 600,000 comparisons for a fraction of a second of video. This creates a massive computational nightmare that grows explosively the second you try to analyze higher resolutions or longer videos. Full 3D attention was, quite simply, way too expensive. But architectures like Timesformer magically bypassed this computational limit. Instead of doing full 3D attention, comparing everything to everything, which has a multiplicative complexity, they used divided attention. They simply separated the operation into 2 sequential steps. First, the model attends only across the time steps to capture the motion. Then it attends only to the spatial patches within the current frame to capture the appearance. By dividing attention like this, the complexity drops from multiplying time and space to merely adding them. It is an incredibly elegant, highly efficient math trick. And just like Timesformer, another model called Vivid proved that decoupling space and time was the ultimate key to efficient video understanding. Vivid uses what's called a factorized encoder. First, a spatial transformer processes each frame completely independently. Then, it takes the spatial classification token, often called a CLS token, which basically acts as a highly compact zip file summary of that entire frame, and passes only those summary tokens into a temporal transformer. This CLS token acts as a perfect, lightweight bridge, completely dodging the quadratic cost of full 3D attention. So we've seen an incredible leap, haven't we? From early models that were totally blind to time, struggling to even tell if someone was sitting down or standing up, to these brilliant architectures that seamlessly fuse space and time using biological hacks and divided attention. So I want to leave you with this final thought.
As AI architectures fully conquer the complex math of time and motion, tracking every pixel and token across the fourth dimension, what subtle human actions, dynamics, and patterns will they perceive next that we ourselves completely miss? Thank you so much for joining me on The Explainer. Keep questioning and keep learning.